In a typical machine learning process, we divide the data set into a training data and testing data, and a usual split would be a 70-30% split. Uh, so in a typical machine learning process, what we do is we train our model on train data set. The train model, we basically the test data set becomes an unknown data set for this trained model. So we test how well this model is performing on test data set. And after that, we estimate the performance by calculating the accuracy. Accuracy is nothing but correct predictions by number of uh, points in test data. So this is a typical machine learning process. Say, imagine we get 95% accuracy. So we can say um, our model is 95% accurate on test data. However, if this model, when it's deployed to production, we cannot claim that the model would be 95% times making a correct prediction. So we cannot say that with certainty. It can behave differently. Probably the model might be giving only 10% accuracy. However, to increase that confidence on our model performance, what we can do is how about uh, making sure that model may perform close to this accuracy that we claim on test data. So what uh, we can do is we can divide the dataset into three parts. First being a train dataset, next is cross-validation dataset, after that test dataset. And typical way of splitting is 60% data into a train set, 20% into cross-validation set, and remaining 20% into test set. So what we do over here is we train our model, so let's say model M, on a train set, and then we we calculate the accuracy of the model on cross-validation data. And after that, we again calculate the say accuracy on test data set. So what happens is before even model goes to production, we are making basically we are making sure whether the accuracy would the model would be performing similarly. So in a way we are testing it like two times. So but over here we are losing 20% of data from our original train set. So is there a way that we can train our model in a better way instead of losing this 20% of data? So, so the next process, this process is called as KFold cross-validation. KFold cross-validation. So what KFold cross-validation does is, say we have the data set, a trained data set, train data of like 80% of original data, and test is 20% of original data. So from a train set, say imagine we make it into say 4 equal parts. So this is the train set, sorry, train set 1 2 3. So let it be d1 d2 d3 d4 train data. Okay. So, uh, how KFold cross-validation works is, mm, imagine, say, if you are doing it on k nearest neighbors. One second. If you are doing KFold cross-validation on k nearest neighbors, k and n. Here, this k and this k are two different things. I'll explain you how. So, uh, what we do in our uh, like KFold cross-validation, we um, find the nearest neighbors on the train set, and then we find the accuracy on our test set. So the better way to do it is, say, train and then cross-validate. So first we start with one nearest neighbor. So here this k, let this be k dash. In k for k fold cross validation, I'll keep it as k dash, and this as k nearest neighbors. Okay. So for one nearest neighbor, I'll train my model on d1, d2, d3, and I'll find the accuracy of this model on my d4. And again, for k equals to 1, I'll train the model on D2, D3, D4, and my cross-validation dataset becomes D1. So again, for here, it becomes D3, D4, D1, and my cross-validation becomes D2. And again, I'll train my model on D4, D1, D2, and my cross-validation set is D3. So what I'm doing over here is I'm I'm training my model 4 times on essentially four different data sets, as we divided our initial data, training data into 4 parts. And each of, like, we take three parts for train and one part as cross validation. So what happens over here is, uh, let's plot the accuracy and the K plot over here. Say K and accuracy. So for k equals to 1, say, but I can plot only one point over here. So what I'd be doing is, for each of these parts, I'll be calculating accuracy over here. So I'll get, say, A4, A1, A2, A3. So I'll take average of all these accuracies and I'll plot here. Say, let's assume we'll get an accuracy of this much. So in my second iteration this is for one nearest neighbor. And next I'll similarly repeat the process for k equals to 2, k equals to 2, and the same process. Initially I'll take D1, D2, D3, and cross validation becomes D4, and here D2, D3, D4, and cross validation becomes D1, and here D3, D4, D1, D2, D4, D1, D2, and this is D3. So for k equals to 2, that is two nearest neighbors, I'll again train my model and find these accuracies A4, A1, A2, A3. So for this, and I'll again find the mean. So essentially, for my k equals to 2 nearest neighbors, I'll get one more accuracy. So I'll repeat this process for different uh, values of k. probably till k equals to 10. So in that case, we'll get a graph so on till k equals to 10. Imagine we'll get our graph maybe maybe like this. So where we get the peak for our accuracy, that becomes the right k. Probably let this be 5. So, and this may be say 90%. So when we are doing our cross validation, what we are making sure is uh, we are finding the right case on the cross validation data set. So after this, we use phi nn and then again find the accuracy on our test data set. Maybe instead of doing this, we'll just find number of correct predictions by total test points and find the accuracy. And this probably we can claim the model in the production might perform this much accurately. Now, is there a way to determine if our model is biased? When I say model being biased, that means whether there is an uh, overfitting or underfitting issue. So what is overfitting and underfitting? Let's say if our data is spread like this, okay, and if we have say this is a combination of let me actually change the colors. One second. Let's say our data is spread like this. Let this be feature F1, this is feature F2. And imagine we have a data point mm, and another data point, say, and we have a green point here and we have our blue point, say, here. So when I do my k-fold cross validation, what I'm trying to make sure is find the k nearest neighbors and then classify the point depending on the majority vote. What if uh, what if my model, let me change the color. Yeah. What if my model fits the uh, uh, on the data like this? So I train my model such a way that the line of best fit it bends to do 100% correct classification. So this is called as overfitting. The model is fitting overly on the data. And what do I call as an underfitting issue? What underfitting does is whatever what underfitting does is if in my data I have majorly positive points and very less negative points. Okay, so what happens is when the model, whatever may be the data point, what if it is always biased to the major class, that is positive in that case, then we call it as there is an underfitting issue in the model. Now, how to is there a way that we can determine overfitting and underfitting issue in a model? Um, there is a way, and the way to do it is we divide our data set into, again, uh, train, cross validation, and test. And we discussed about accuracy, right? That is the correct predictions by total number of data points. Here, so as we found, as we have determined the accuracy, error becomes 1 minus accuracy, right? So for the train set, we'll find training error, and for our cross validation data, we find cross validation error. And we plot these two errors for different values of k. So the plot for this would be my train error. As k increases, my training error increases. This is train error. And we saw the plot between accuracy and k, right? For accuracy and k, we observed as k increases, we find the peak of the accuracy, and eventually when k increases more, the accuracy reduces. This is the determined as correct k. So when we have an accuracy plot like this, the inverse of this would be an error plot. So my cross validation error plot will be like this. Sorry, let me redraw it. Not again. You ideally it will not meet like that, but let me redraw. Yeah. So this will become my cross validation error. So wherever there is very less error on my cross validation, that becomes the right K. And on the left side of this area we call it as overfitting, and this area is called as underfitting, which means when cross validation error is high and my train error is slow, then we will have overfitting issue. When cross validation error is high and train error is also high, then we'll have underfitting issue. So we can find if for the train model whether we'll be having an overfitting and underfitting issue by this. So for this right k value, we'll find the accuracy for the model on the test set. Thank you.